So welcome to section 3.2 notes. In this section, it's going to be very rewarding because we're going to start getting away from the definition of the derivative, so using this formula of the limit as h approaches 0, and learn some of the basic rules of differentiations that are just going to make our life so much faster when we look for derivatives, and therefore it's going to allow us to go further in concept understanding and just the richness of the questions we will be able to ask. The other objective today is to learn sine, the derivative of sine and cosine, and also of the exponential function. I think of that as learning some new vocabulary. If you do that in a language, then your writing is going to be that much richer, and we want to know these derivatives by heart so that we can use them in further problems. And finally, we'll talk about rates of change. So what is a rate of change? It's how much something changes, and we'll talk in particular about velocity today. But the slope of a graph, that's a rate of change, because it's the rate at which the height is changing. So how much is the height changing? If a graph is very slopey, then the height is changing very fast. So the rate would be very high. So rule number one, we can see that in two different ways. We can see that either algebraically, which is what we're going to see in the proof, or we can think about it in terms of geometry. So before we start, I'd just like to bring this on, which I wrote on the whiteboard, which I would always write when we do these notes in class. So find a place to do that. In particular, the blue one. For the purple one, we'll talk about it again in a few minutes. But the fact is, when we talk about algebra, we will think of derivative. And when we switch to this other world of math, which is geometry, then the equivalent is the slope. And there's like a bridge between these two concepts, and the better you are at crossing that bridge, the better you will be at figuring out how to solve some problems. And so basically, every time you see the word derivative, you can in your head think of the word slope instead, and vice versa. If there's a question about slope, you might in your head think about derivative, and it may give you a key as to how to solve the problem. So I put that in a box with 4 little screws at the corners to show that this is really important for you to get comfortable with, something you have to get familiar with. The next one will come up a bit later, but the fact that if the derivative is 0, so again, that's an algebraic expression, something equals 0, that corresponds in the geometrical world to a line, a tangent line that is horizontal. So the derivative of a constant function f of x equals c is f prime of x equals 0. Indeed, if the function is constant, then the slope is 0. That makes total sense. That's the geometrical understanding. If we want to think about it algebraically, we will use the definition of the derivative f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. And since f of x is always c, no matter where you look, it becomes just c minus c over h, which is 0 over h, which is 0. And now we can plug in h equals 0, and we see that, well, we're not plugging it in anywhere because there's no h's left, but that's where we proceed to do direct substitution, and the answer is 0, indeed, as we thought of geometrically earlier. The second rule is the power rule. So I'll call it the power rule from now on. I'm never going to talk about these numbers. They don't refer to anything. When you have a monomial, so a power of x, the derivative is f prime of x equals n times x to the negative 1. So we can show that algebraically. It's this proof here, which is non-essential, so I'm going to talk about it, but it's not necessary that you even copy it if you don't want to. The derivative of x is this, by definition of the derivative. And the step that we go on from here uses the binomial theorem from Algebra 2. So if you have, it probably was either a plus b to the power of n or x plus y to the power of n. But in any case, what this is going to be when you expand this binomial is x to the power of n plus n times x to the n minus 1 times h, and so on and so on. The rest won't matter in the end, but these two first terms definitely matter. And then we have minus x to the n, just like we had here, and it's all over h, like here. So things cancel out very nicely. X to the n cancels out here and there. I put a kind of a slash crossing, and then I did backslashes for canceling the h. Once we got rid of this and that, there's at least one h in every single term, from the first one here to the last one there, and so they cancel out. Each of them cancels out with the h at the bottom. Therefore, we are left with an expression that has n times x to the n minus 1 plus a whole bunch of stuff, and all of these terms have at least one h in them. So when I do direct substitution, when I plug in h equals 0, all of these become 0, and we are left with just n times x to the n minus 1. So that is what we wanted to prove. This proof only works when n is a positive integer, but we will see later in the next section that this power rule is also true for any value of n. You can take negative values of n, you can take fractions for n. It's always the same. It's always the same rule. So we're going to consider that we agree with that. It's always this rule, no matter what n is. And we'll see a few examples right now. So we could have asked you last class to find the derivative of f of x equals x cubed. Chances are you did it at some point, either in pre-calculus or in the exercises this year, and you would get to that answer. But now that we have the power rule, it's so much easier. The derivative of that, what we say is you put the 3 in front, and then you subtract 1 to the exponent. So it becomes 3 times x to the 3 minus 1. So there's the answer. It takes literally 2 seconds to solve instead of 2 or 3 minutes. If I'm looking for the derivative of f of x equals 3 over x to the 4th power, this is not quite in the form that we want, but we can rewrite that using algebra only. This is the same as writing it like that. And now this has the form that we are interested in, so we can apply the power rule. The power rule will tell us that you bring the negative 4 in front, so 3 times negative 4 becomes negative 12, and then negative 4 minus 1 is negative 5. So be careful when you have negative numbers at the exponent. Subtracting 1 makes it look bigger, right? It's negative 5. It's not always getting closer to 0. One more thing here, you can see that in the first example I used the notation f prime. Here I used the notation dy dx. Here I used the notation ddx times f of x. So all these are exactly ask for the same thing. You have to get used to these different ways of writing the derivative. Last example of the power rule. Again, y equals square root of x cubed is not in the form that we need, but using algebraic properties only, we can rewrite this as y, or f of x, equals x to the power of 3 over 2. I did not do any calculus yet, but now I will. The derivative is n. Here n is 3 over 2. So n times x to the n minus 1. And if you want to rewrite that as a square root, then it's f prime of x equals 3 over 2 times square root of x. That's it for the power rule, a very important one. The derivative of c times f of x here is c times f prime of x. The derivative of g of x plus h of x is g prime of x plus h prime of x. These two rules together tell us that the derivative is quite well behaved. If we have a multiple in front, it's still easy to find the derivative. And if you have two functions that are added, you can just take each one of them and take the derivative separately and then add the derivatives together. So in fact, rule number 3 we've used already before. C times f of x we've used in this example right here when we had 3 times x to the negative 4. And the derivative, you can just ignore the 3 and you multiply it in front. This is a rule we won't think about much, but we're using it all the time in AP Calculus AB. Here's an example. This is a function. It has 1, 2, 3, 4 terms, and each of them you can take the derivative separately. So the derivative of 2x to the 5 is going to be 10x to the 4. The derivative of 3x squared is going to be 6x. The derivative of 7x, you can use the power rule here, but you can also think of this entire group here. It's just a line. It's the line 7x minus 5, so the derivative of this entire group is 7. But anyway, you can also use the power rule and figure out that 7x, the derivative is 7. And then negative 5, that's a constant, so the derivative is 0, as we saw earlier. So you put all of these individual derivatives together, 10x to the 4 minus 6x plus 7 minus 0 if you want, and you have the answer. So key understanding. This is the second part of the thing that you need to copy and put little screws to say how important it is. If you understand that, fundamentally understand this concept, then from starting at 0, knowing no calculus, to reaching 100, knowing everything AP Calc AB has to say, you've just raised your level by 2 if you really understand that a horizontal tangent means the derivative equals 0. So let's see the question. Find the coordinates of the points on the graph of f of x equals half x cubed minus 6x where the tangent is horizontal. So we want the tangent horizontal. That means we want to find the line where the slope is 0, where the derivative is 0. So very interesting. Let's look for the derivative and set it up equal to 0. Derivative equals 0. So we can use the power rule. F prime of x is going to be, so I bring the 3 in front, so this is now 3 over 2 times x to the power of 3 minus 1, so x squared. The derivative of negative 6x is negative 6, that's just a line. So here's my derivative. And because we're looking for places where the derivative is 0, I set this equal to 0. And I solve, and I get 2 points, or 2 values of x where this happens. So the points are, let's take x equals negative 2 first. The points are negative 2, 8. And then if x equals positive 2, it's the point 2, negative 8. I should put a little parenthesis here, like that. So where did I plug negative 2 and 2 in order to find 8 and negative 8? I plugged it in y, or f of x, here, because we're looking for a point, so the point is x, y. What happens if you plug it into f prime instead? Well, you're going to find the derivative and try it, but you're going to find 0, because that's what we were looking for. Where is the derivative equal to 0? So it's incorrect at this point in the exercise to plug negative 2 and 2 in the derivative. We're looking for the point, we're not looking for the slope. At the end, here's a sketch of the graph and what it looks like so that it can give you an idea of what we were working with, but we could solve all of this without thinking, without having any idea of what the graph looked like. Okay, so here are 2 derivatives that we're going to have to know by heart. The derivative of sine is cosine, and the derivative of cosine is negative sine. So this is interesting because it looks like they kind of reflect on each other. The derivative of sine is cosine, then the derivative of cosine is negative sine. If we take the derivative of negative sine, it's going to be negative cosine, and then if we take the derivative of negative cosine, it'll go back to sine. So it's kind of, there's a fourth step. If you take the derivative, it's a cycle of these values. I always memorize this one, the derivative of sine is cosine, and then I know that the other one has a negative in front. So, little exercise here. What's the derivative of f of x equals 3x squared minus cosine x? We can treat these two terms separately. The derivative of 3x squared is 6x, and the derivative of cosine x is negative sine. So minus cosine x is going to become plus sine x. And that's it. If you think of sine x, let me just try if I can make a kind of a sketch. Sine is the one that does like that. So we can see the slope at the beginning is positive. And if you think of cosine, it starts here and then it drops, right? So we can see that it makes sense. The derivative of sine is the slope here, it's positive 1. And what's the slope of cosine up here? It's 0. And indeed, if you plug in negative sine of 0, you get 0. You can think about that more later when you're a bit more comfortable with these two formulas here. The last one that we introduce is the derivative of f of x equals e to the x. And the amazing answer is that the derivative is e to the x itself. This is why maybe before calculus you've heard that e is an important number in math, but you may have thought, well, pi is certainly more important. Well, e is just as important and amazing as pi. Pi is the number that you find amazing when you do geometry. It shows up in circles and many other places. E is the number that's amazing if you do calculus. And one of the main reasons for that is this fact here, that the derivative of e to the x is e to the x. And it's, to a certain extent, it's unique. It's almost unique. The only other functions that are like that as well, whose function and derivative are equal, is if you take 2e to the x, or 3e to the x, or 27.4e to the x, the derivative is going to be itself, the function itself again. But these are the only one. Of course, f of x equals 0 is also, it's also true, but that's really uninteresting. It's taking 0e to the x. So this is e 2.718. It's a value that you may want to have a vague knowledge of, just like you know pi is 3.14. So let's talk about velocity now. First, we're going to review average velocity, which is something you've known since middle school probably. The average velocity is the change in position divided by the change in time. So if you know the position of an object at two different times, then you can find the average velocity between these two times. Here's an example, a billiard ball is dropped from a height of 20 meters. Its height, s in meters, after t seconds is given by the position function s equals negative 4.9 t squared plus 20. Find the average velocity over the time interval 1, 2. So we're going to want to find the position at 2 and the position at 1 and find the difference. And then we're going to divide by the change in time, which here it's 2 minus 1. So with a calculator, you can find that s of 2 equals 0.4, s of 1 equals 15.1. So that makes sense. It started at a height of 20 meters. After 1 second, it was at 15 meters. And after 2 seconds, it's almost hitting the ground. We divide by 2 minus 1, and we get that the average velocity of the billiard ball was negative 14.7 meters per second. There's a negative, we'll talk about it in a minute, but that means it was going down. In other situations, it means it's going left. If you think of graphs, the arrow always points in the positive direction, so if you get a negative number, it means either it's going down or it's going left. The general formula for free-falling objects on Earth is given here, and g is negative 9.81 approximately. So when you do 1/2 of g, you get negative 4.9. If you are studying physics, you may have seen this negative 4.9 in different places. And actually, it was right here, because the billiard ball was a falling object. V0 is how fast the object is falling at the beginning, and S0 is how high it was at the beginning. So in the billiard ball example, we dropped it from a height of 20 meters, and that's why so 20 meters, that's why there was plus 20. We just dropped it, so it was plus 0t. If we had threw it downward or threw it upward, then there would have been a value here for V0t. Now, when we do calculus, we're going to be focusing on the instantaneous velocity, how fast something is moving at an exact moment in time. If the position of an object as a function of time is s of t, so if you know the function of the position, then the instantaneous velocity is the derivative of that function with respect to t. When we just say velocity, we mean instantaneous velocity. So the one we always emphasize is if we talk about average velocity. But if we don't say average or instantaneous, then it means instantaneous. Instantaneous velocity is the thing that you see when you're in a car and you're just looking at the speedometer. That's what you see. It's how fast you're going right now. So it changes all the time, right, when you're in a car, which makes it much harder to find than the average velocity if you're working with equations or if you're not sitting in the car itself looking at the speedometer. So, quick little example. The distance a car has traveled after t seconds is given by the simple function here. S of t is 2t squared, and this is true for t's between 0 and 8 seconds. So how far has the car traveled? This is just what is the distance the car has traveled, so it is simply function s. That's the distance the car has traveled, s of t. So you just plug in 5, so 2 times 5 squared equals 50, and it's 50 meters. When the question is the velocity, that's a rate of change. How much is the position of the car changing after 3 seconds? You have to first look for the derivative of the position. So the derivative of 2t squared is s prime of t equals 4t. And now I plug in t equals 3, and I get 12. One thing I'm thinking about here is always remember to take the derivative first and plug in the value second. If you plug in 3 here first, then you'll just get a number and the derivative is 0. So that makes no sense. The derivative would always be 0. You want to take the derivative first and then plug in the number. And last 2 comments. The velocity can be negative. If it's negative, it means the object is going left or it's going down. Secondly, the speed. In real life, we may say speed all the time. In physics and math, you want to be careful. The speed is the absolute value of the velocity. So that means I can have a velocity of negative 12. My speed is positive 12. So it's the absolute value of the velocity. All right, that's it for section 3.2. Thank you for listening.